Welcome back everyone. In this lecture actually we will talk about finite sets, and then first we will see that how one can define cardinality of the finite sets. So, let us recall the definition of finite sets. We say X is finite if X is either empty or we have a bijective map from X to this I n, where I n is just 1 to n. Okay, so, now we have a very basic question here. One can actually think about, so if we are actually having, let us say, finite set X, then the way we have defined, we have a bijective map from X to I n. So, now the question is, so why the cardinality of X needs to be well defined. Okay. So, let us make it very rigorous. So, the bijection that actually we have from X to I n actually tells us that how one can actually count the elements of X. So, that is what the bijection means. So, let us actually rewrite this bijection as follows. So, we write it from, let us say, from I n to X. So, then this bijection actually tells us that okay, where 1 actually maps and then where the 2 actually maps and so on. So, that means that what we have done here, we have just listed this capital X as x 1 etcetera x n. So, we have given one procedure to count the elements in X or the list the elements in X. But the problem here is actually, so this procedure that we have given, it is actually a choice that we have made. Okay. So, now one can ask that okay, what if actually someone actually comes up with some other way of listing or some other way of counting, why that should actually lead to actually same counting. Okay. So, that question is already there. So, if we put it in more mathematical term, we can actually say that so one can actually come up with this f from I n to x, which is bijection, and one can come up with another map from I m to x, which is also bijection. Okay. So, now there is no reason to believe that to begin with n should be equal to m. Okay, that is what we are actually trying to convince ourselves. So, intuitively it is clear that because we are actually counting the same set X, so there should not be two ways to count. Okay. The final number, the total number of elements in X should be same, but in theory we can actually have this two ambiguity way of counting. Okay. Counting in two different ways. Why it should lead to same number? So, that question is there. So, basically what we are asking, if we have two bijections from I n to x and I m to x, then whether does it imply n equal to m. Okay. And if you think about it, this can be reformulated as follows. So, by taking this bijection from I n to x and then x to I m, you can take this f map and then you can take this G inverse map. By composing that, we will have this map G inverse f from I n to I m, and that map is indeed bijection. And now what we are indeed asking, so suppose you have a bijection from I n to I m, why that will imply n equal to m. Okay. So, then why that implies n equal to m. So, it is a legitimate question because we never care about this question, but once you formulate this mathematically and we can ask this question. This question actually leads to well definedness of the cardinality of X, and we want to say that in this case that when you have a bijective map from X to I n, the cardinality of X you want to say it as n, because in the previous lecture we were actually only comparing given two sets whether they have same cardinality or not. Okay. But now we want to define the cardinality of x to be n. So, for that we need to make sure that we cannot have two different bijections from two different sets I n I m to x. Okay. So, that is what we need to do. So, for that we will actually make some small lemmas. So, this indeed can be proved using mathematical induction, because any statement about natural numbers, so one should be able to use mathematical induction to prove. Okay. So, here it is indeed a statement about natural numbers only. So, we will use mathematical induction to prove this. So, to prove this, what we are going to do? We are going to split up actually this bijective statement about injective and surjective. So, if you recall, you have one side is I n, one side is I m. So, what is I n? I n is just 1 to n, sorry 1 to n, and I m is just 1 to m. So, now for example, if you have a injective function from I n to I m, then that means, so the cardinality of I n should be less than or equal to cardinality of I m. So, that means n should be less than or equal to m. So, that means whenever n is greater than m, then we should not have any injective map from I n to I m. So, let us make that as lemma. So, if m is less than n, so then we prove that there is no injective map from I n into I m. Okay, because the size of I n, intuitively it is clear that it is n. So, n should be, like if there is an injective map, n should be less than or equal to m, but here we assume that m is less than n. So, that means we should not have injective map. Okay. So, the more important point here is how to prove this. Okay. So, the proof of this just uses mathematical induction. So, that is the best way to prove, and so what we will do, we will actually treat this as statement about m. Okay. So, there are like two induction that you can do, either you can induct on n or induct on m. Okay. Now, what we are going to do, we are going to induct on, so maybe one can also do induction on n plus m, that is also possible. Okay. So, let us say we are inducting on m. Okay. Induction on m. Okay. So, I am treating this as the statement about P of m. So, given m and given n, okay. So, sorry, given m for all n such that n is greater than m, we cannot have a injective map from I n to I m. So, that is the statement P of m. Okay, let me write it. So, P of m is, so m is fixed, okay, for a given m, okay, there is no injective map from I n to I m for all n greater than m. So, this is the statement. So, let us verify this for the initial step. So, when step 1 we take m to be 1. Okay. If m is 1, you can see that already we are done, because if n is 1, that would imply that n is greater than 1, that would imply that you have n is greater than or equal to 2. So, then I n will be at least 1, 2, etcetera n. So, it has at least 2 elements, okay. And you cannot have injective map from more than 2 elements to singleton set. Okay. This I m is singleton. So, it is clear that P of 1 is true. Okay. So, now let us go to the step 2. Okay. Let me just draw a diagram. So, the step 2 actually talks about you assume the result is for true for assume P of m is true, okay, then we try to prove it for m plus 1, or we can assume it for m minus 1 and then prove it for m. Okay. So what happens? So let us say I have an injective function, okay, we want to prove climb is P of m plus 1 is true. Suppose not. If not, what happens? There exists a function f from I n to I m plus 1. Okay. So, for some n greater than m plus 1. Okay, this is actually happened. So, now you have this injective map from I n to I m plus 1. So, you have this which is 1 to etcetera n, and then you have this bigger one 1 to etcetera m plus 1. Okay. So, you have this function f. So, now note that in case n is mapped to m plus 1, then what would happen? So, let us deal with this case 1. So, the case 1 I am saying that n is mapped to m plus 1. So, case 1 is that f of n is exactly m plus 1. So, in that case what we can do, we can just restrict the function to the remaining set. Okay. You can restrict to I n minus 1, and then which is a map from I n minus 1 to I m. Again restriction of a injective function will be injective. So, this is indeed an injective function. Okay. So, what we have done, we have just removed this part, and the remaining part we just focusing on, and that f restricted to that is an injective function. So, now because it is an injective function, and what happens to my n minus 1, if you think about it, this is again greater than m, okay, because n is greater than m plus 1, and we have produced indeed one injective function which is a contradiction. Contradiction to the statement P of m is true. P of m is true. So, that tells you that this case you cannot have. So, that means we will have the case 2. The case 2 will be f of n is going to be some k which is not equal to m plus 1. So, the k has to come from 1 to m. Okay. So, pictorially speaking, so you have this 1 to etcetera n, and then you have this 1 to k etcetera m plus 1. Okay. So, now what we have noticed? We have noticed that this n is mapped to this k. Okay. So, when n is mapped to m plus 1, it was easy to delete them and then look at the remaining map, but here what to do? And if you think about it, so we can actually produce a new map, because this is an injective map. So, you do not disturb rest of the maps, you just take this particular thing. So, you take this particular assignment n goes to k, okay, take this assignment and then just interchange this. So, now what you are going to do, like so you know this m plus 1. So, this is again mapped by some r here, okay, this r is going to map to this, because you have an okay, all we have is injective map. So, it could happen that it is not even mapped. Okay. So, if it is okay, so again maybe that should be the case 2. I am going to assume this is true, and then in case 2.1 will be like f of n is k and f of R is m plus 1. Okay. So, it could happen very well. In that case, what you do, you just interchange them. Okay. So, just define G, which is a map from I n to I m plus 1. So, where G of any I is going to be f of I when I is different from R and n, and G of R is now you define it to be k, and then define G of n to be m plus 1. You just interchange them. Then it is easy to see that G is injective. Okay. So, because we did not disturb rest of the map, we only disturbed these two and we just interchanged them. So, now you have gone to the previous case where G of n mapped to m plus 1. So, now you can delete that and you have produced injective map from I n minus 1 to I m. So, it goes back to the case 1. So, in this case also we are done. So, now what will be the second case? The case 2.2 will be again f of n is k, but m plus 1 is not in the image of f. Okay. So, it could happen that it is not even in the image, but then what you can do, you can simply like remove this, or again you can actually interchange, no issue. So, we have this 1 2 etc. n, and then you have this 1 2 k etc. m plus 1. We have this map, injective map. So, now what we assumed? We assumed that this n is mapped to k. Okay. So, now what you can do? You can actually define this G again from I n minus 1 to I m, because that is what we wanted to do like before. So, now you define this G as just G of j for all j, okay, which is different from n. Okay. So, now we already assume that m plus 1 is not in the image of f. So, that means the image is going to be contained in only in I m. Okay. So, that means image of f is contained in I m. So, then it is clear that the map that we actually defined here. Okay. So, it is already like okay. So, even for G of n, it is, you can take it to be k, there is no issue, because so basically G is same as f. So, then that would imply that G is injective. Okay. So, now you have constructed that a function from okay. So, we have actually constructed a function from I n to I m. So, we wanted actually function from I n minus 1 to I m. So, now what we can do? We can actually simply remove this. So, yeah, we can actually remove this, there is no issue. So, we do not define G of n. So, we just take G restricted to I n minus 1 to f restricted to I n minus 1, which is a valid function from I n minus 1 to I m. Okay, because the image does not contain m plus 1, and the restriction of injective function is injective. So, this is again injective, and you got a function from I n minus 1 to I m, and which gives you contradiction to P of m. Okay. So, in both cases we have actually produced contradiction. So, that means the original statement that there exists this injective map from I n to I m plus 1 is not true. So, we proved that we cannot have indeed injective map from I n to I m. So, now what if injective map is there? If there exists injective map from I n to I m, so then this analysis tells you that immediately we get that m is greater than or equal to n. Okay. So, there is no way that m is strictly less than n, because if m is strictly less than n we cannot have a map. So, that is why we will get this. So, now let us actually prove that we cannot have any onto map from I m to I n when m is less than 1. So, here is the second statement of the lemma. Okay, maybe you can call it as lemma 2, that if m is less than n, then there is no onto map from I m onto I n. Okay. So, the proof of this actually goes back to lemma 1, because if you have a onto map from I m to I n, let us say it is onto surjective map. So, then what you can do, like given I in I n, one can look at f inverse of I and then take the minimum of this and then call it k I. So, now you can define this map G from I n to I m. So, where I goes to this k I, which is nothing but the minimum of f inverse of I, and it is not difficult to see that this G is injective. So, that is because whenever we take I different from J in I n, then it is clear that the inverse images f inverse of I intersection f inverse of J must be empty. So, that would tell you that immediately k I should be different from k j. Okay. So, that means this map G must be injective. So, now we have produced injective map from I n to I m, and which is a contradiction to our previous result, because we proved that whenever m is less than n, there is no injective map from I n to I m. Okay. So, this tells you that whenever you have an onto map from I m to I n, then we should have that m is greater than or equal to n. So, now let us go back to our original thing. Let us say we have a bijective function from I n to I m. So, this is a bijective, let us say. So, then we can easily see that f is injective. So, that implies m is greater than or equal to n. Okay. So, the proof of this is that f is injective implies m is greater than or equal to n, and f is surjective, that implies n is greater than or equal to m, and this together will imply m equal to n. Okay. So, now we have actually rigorously verified whenever you have a bijective function from 1 to n to 1 to m, then n must be m. Okay. So, that means I can define cardinality of given finite set if x is finite. So, then you define the cardinality of x to be 0 if x is empty, and you define cardinality of x to be n if there exists a bijective function from I n to x. Okay. So, this is now well defined, there is no ambiguity in the definition. Okay. So, now one can actually immediately check that a subset of a finite set must be finite. So, that is not difficult to check, maybe I will leave it as exercise. Let A be finite and B is subset of A, then B is finite, and not only that, the cardinality of B can be at most cardinality of A. So, now since the cardinality of finite sets are natural numbers, we can compare natural numbers. So, with that comparison, using the order property, we can actually write cardinality of B is either less than or equal to A and so on. So, now we can actually write down many equivalent versions. Okay. The most important practical application of all this will be the following. So, we say that two sets are actually having same elements. Okay. Maybe like we will actually look at only the functions defined from same set to same set. So, let us say A is finite set. So, then the following are equivalent. Okay. The first condition is that you have f from A to A is bijective, and the second condition you have f from A to A is injective, and the third condition f is from A to A is indeed surjective. Okay. So, if you have same cardinality sets, then any injective function from one to another will be bijective. So, that is what it says. Okay. So, as a corollary you can actually take as a corollary we can take that cardinality of A equal to cardinality of B, both are finite. So, then one can say that f from A to B is bijective, f from A to B is injective, and f from A to B is surjective. Okay. And this is most useful result to know, like it will be used in many places of mathematics, okay, without even any mention. Okay. They just simply use it. Okay. So, the way you prove it, so you have to kind of compare the cardinalities. Okay. So, for example, like if f is injective, then what would happen? The cardinality of f of A is same as the cardinality of A, because f is actually a bijective function from A to f of A. So, now since the cardinality of A is same as the cardinality of f of A and f of A is subset of A. So, that would imply that f of A must be equal to A. Okay. And that actually tells you that f has to be surjective. Now, if you take f is surjective, so then we need to actually say that f is bijective. Maybe I will leave that as exercise, that prove actually 3 implies 1. Okay. It is not very difficult. So, one has to think about little bit of this. Okay. So, now we can actually give again some equivalent definition of finiteness. So, maybe I will state it as exercise, it is not very difficult. So, you start with a set. So, then the following are equivalent. So, A is finite. So, that means there exists a bijective function from A to I n, or A is empty. Okay. A empty case is nothing to worry. And now, what we can say, like if there is a bijective function, then we can also have an injective function. So, there exists injective, okay, let us say non-empty set, injective map from f to a to in. And in that case you can say that the cardinality of A is less than or equal to n. The third condition, there exists surjective map f from in to a. In that case again n is greater than or equal to the cardinality f. Okay, and these three are equivalent. So, if you want to prove something is finite, you find a surjective map from in to a, then it becomes finite. Similarly, you find a injective map from a to in, and that also kind of tells you that a is finite. And this thing, even though seems to be like easy thing to see for the finite cases, and this is actually very helpful when we go to the infinite sets. Okay. So, maybe I will stop here and we will continue with the infinite sets in the next class. So, I will first start with countable and countably infinite sets, and then later we will move to actually comparing different infinities. I will stop here. Thank you.